Hello everyone, I'm Cong Miao from Tencent. Today I'm going to share our mega-scale WAN traffic engineering at the granularity of cloud virtual instance in Tencent. The title is MegaTE, extending WAN traffic engineering to millions of endpoints in virtualized cloud. As one of the world's largest cloud provider, Tencent Cloud allows millions of tenants to run virtual instances at virtual machines and containers with the same data center infrastructure. Such cloud paradigm achieves significant cost-sharing benefits for cloud tenants. Under the hood, cloud provider always own and operates ones which connects those data centers to provide the cloud service globally. The ones are the workhorse of those millions of cloud applications with the exchange of terabytes of data every day. Those cloud applications may have different requirements of quality of services. For example, the Q's class 1 is the highest priority with service level agreements of Fortnite. It contains control traffic and a few critical services. Those applications are always time sensitive. Q's class 3 has the lowest Q's requirement. It's always for heavy bulk transfer. In this talk, I will present a first-of-its-kind system called MegaTE that extends T systems to meet the requirements of millions of virtual instances. Let me start with the background. In conventional T systems, for each T period, the routers in the data plane collect the flows in an aggregated fashion from data center servers and send them to the bandwidth broker. Sends the bandwidth broker forwards the network topology and aggregated traffic demand to the T optimizer, which calculates the optimal traffic allocations. The controller then receives the optimized configurations and adopts top-down centralized control to push configurations back to the routers. To ensure immediate synchronization of the T configurations once they are generated, a persistent connection is established for each router and SDN controller. To maintain the connection, a heartbeat packet is periodically exchanged to keep it alive. Obviously, the conventional T systems operate only on the network router. They cannot distinguish the traffic from containers, resulting in the network results unable to align with the specific needs of container. Specifically, there are always multiple traffic flows initiated from the same containers entering the one through the edge router. The hash function of the traffic splitting in the router may route the traffic to different paths. This would result in that those flows have different packet latencies, harming the application level performance. We measured the packet latency of 4 instances in production. It shows that latency has a large variance and is not stable. We zoom in one of the virtual instances and find the latency is mostly clustered into 2 groups around 40 milliseconds and 20 milliseconds. Ideally, tuners require the flow between instance pairs to be running on the low latency path. To address this issue, our goal is to extend the existing T system to involve millions of virtual instances. In this way, despite of complex cloud environment, we can precisely accommodate to fine-grained requirements for each instance. However, it's not trivial to achieve this goal. If we assume that a traffic flow from the tenants can be distinguished on the router by inserting flow entries, accommodating to millions of instances requires installing millions of flow entry in the routers. However, the number of flow tables in the router is limited and always static. It's not practical to install flow entries for all instances. Therefore, the flow should be identified and segment routing information should be inserted before it leaves the server. Another challenge is the computational complexity involved in formulating optimal T decisions at the control plane. Traditional T systems manage traffic on a few thousand nodes. In contrast, MegaTE must manage the traffic between millions of endpoints. magnifying the problem scale by 3 orders of magnitude. It's hard to solve the T problem in a timely manner without compromising the accuracy. Furthermore, conventional T system adopts top-down control loops that uses persistent connection to push T configuration to routers. When extending the existing system to involve millions of endpoints, conventional control loop will require millions of persistent connection at the controller. This approach consumes a lot of resource and overwhelms the control plane. We then present our MegaTE system in 3 parts, including rearchitecting T control loop, two-stage T optimization algorithm, and the eBPF-based segment routing. To address the control loop issue, MegaTE rearchitects the T control loop by trading data plane consistency for control plane scalability. Specifically, it uses a bottom-up approach in which the controller is replaced by a T database where endpoint server pulls the configuration asynchronously to achieve the eventual consistency. This approach does not require the controller to maintain persistent connection with millions of endpoints and introduce little overhead as the controller. Specifically, the T optimizer updates the T configurations and stores the new updates into the database. Those endpoints queries the cloud database to check for the latest T configuration version in a different time. Upon detecting a discrepancy between the version number of its current configurations and that provided by the database, the endpoint pulls the new T configurations and proceeds to update its settings accordingly. Those endpoints will coverage on a consistent view of the network states over time. As the control plane, since we address the T problem at the granularity of the virtual instance endpoints, we assume that the traffic flow from instance cannot be arbitrarily divided. The main reason is that there will always be multiple flow between an endpoint pair. Routing those flows from the same TNARs over multiple paths would lead to unstable latency, degrading the application quality of experience. This turns the conventional multi-commodity flow problem into an NP-hard decision problem. The audience can refer to the paper for more details. The hyperscale network topology and the NP-hard nature makes the maxi overflow problem extremely complex. To address this challenge, we observe that MegaTE topology consists of 2 distinct layers of connectivity, where the first layer represents a highly meshed topology among the network sites, and the second layer includes a pair of network sites, each forming a hub that connects to multiple endpoints. We propose a 2-stage optimization algorithm to solve the problem on each layer separately. On the first layer, we first aggregate the endpoint flows connecting to the same site pair and solve the max site flow problem. Since the flow at the router site can be satisfied in part, it becomes a multi-commodity flow problem and the number of nodes is a few hundred. We can use the existing T approach such as linear programming to obtain the bandwidth allocation. On the second layer, we need to solve the traffic allocation for the endpoint pairs given the bandwidth allocation generated in the first layer. For a specific set pair K, given the bandwidth allocation FKT and bandwidth demand set among endpoint pairs DKI, the max endpoint flow problem is to select a subset of the bandwidth demand whose total traffic is closed to without exceeding allocated bandwidth. The max endpoint flow problem is a typical subset sum problem, which is NP-hard. We propose a novel semi-dynamic programming technique, faster SSP, that includes 4 procedures to significantly reduce complexity while allowing for controllable precision in the solution. To address the challenge at the data plane, we leverage the eBPF to handle individual flow. The eBPF enables users to customize complex operations inside the kernel to process and trace packets. Each eBPF program should be attached to a hook such as traffic control, which will be triggered by a kernel event. The eBPF maps are key value database used to store eBPF states, enabling communication among various eBPF programs and between eBPF programs and user space process. We firstly identify the instance of the traffic flow. We attach the eBPF program at the syscall hook to collect the process ID and the instance ID. Once the instance runs a process and then stores them into the map, once the process creates a socket connection for packet transmission, it will trigger another eBPF program to collect 5 tuple of the packet and process ID. With this information, each 5 tuple item of a packet will be accurately mapped to its originated virtual instance. We then attach the eBPF program at the traffic control hook to collect the traffic volume of each 5 tuple based on the map of instance ID and 5 tuples stored in the map. The endpoint agent will periodically initiate a user space process to collect flow data. In this way, we can achieve flow collection at the instance level. Once the centralized controller calculates the optimal path decision for each instance after the T optimization, it will notify the endpoint agent to initiate the process to store the instance ID and packet paths in the eBPF map. Upon receiving a packet, the eBPF program attached as the TC layer firstly captures the 5 tuple to obtain the optimal path of the packet. Then the path of the packet is inserted into the packet header. Specifically, we let the segment routing header be inserted subsequent to the VHLAN header. In the header, the hop number field represents the total number of hops. The hop array is a sequence of next hop, specifying the detailed path of the packet traversing the WAN. The root site in the WAN profiles the packet and obtains the hop information to forward the packet to the specific path. We finally present the gains of MegaTE. We obtain traffic metrics as the granularity of endpoints from production and evaluate the performance by increasing the number of endpoints. We compare MegaTE against the existing T schemas such as NCFlow and TEAL. We observe that for the network topology with about 1,000 endpoints, both NCFlow and TEAL takes 5 seconds to complete TE computation. In contrast, MegaTE completes the flow allocation more than 22,000 endpoints for the same optimization runtime, supporting 20 times more endpoints. Meanwhile, MegaTE supports a satisfied demand that is closer to the optimal, indicating the superiority of our algorithm. We then evaluate the MegaTE on the failure scenario. For the network with about 1,000 endpoints, we observe about the 4% gap of the satisfied demand. As the network topology becomes larger with a total of about 5,000 endpoints, the gap between the satisfied demand by NCFlow and MegaTE increases, reaching a value of 8%. The main reason is that NCFlow takes about 100 seconds to recompute the new traffic allocation. A large portion of network flows will be dropped during the T recomputation period. MegaTE takes less than 1 second to recompute new traffic allocation to reduce the packet loss. MegaTE has been deployed in the production WAN of Tencent to serve millions of T nodes for more than 1 year. We compare our MegaTE with our traditional T approach, which does not differentiate the queues class of endpoint flows. For those time-sensitive applications such as video streaming and financial payment, MegaTE can always allocate the traffic to the optimal path to reduce the network latency. Especially for application 1, the latency is reduced by more than 51%. For those applications in the cloud, MegaTE can appropriately allocate the network traffic to the path meeting its queue's requirements. For the application with higher quality of service demand, such as application 6, the average availability maintains more than 4.9 and 5, greatly exceeding its availability requirements of 4.9, while for lower queues requirements application, such as application 7, MegaTE can still meet its requirement. In conclusion, MegaTE is the first of its kind system to satisfy the needs of each fine-grained traffic flow at the virtual instance level. MegaTE re-architects the T control loop from top-down centralized control to bottom-up asynchronous database query. MegaTE is built on the synergy between control plane and data plane. Simulation results show MegaTE supports 20 times more endpoints with a similar runtime compared to existing T system. Production results show MegaTE reduce the latency and maintain high availability for high priority applications. That's all. Thank you very much.